With the urge to reduce fossil fuel emissions, it is critical to develop sustainable energy storage technologies. For one, this enables the electrification of transport, and two, this enables the use of renewable energy sources like wind and solar because these are intermittent power sources. So, lithium-ion battery production is expected to increase exponentially in the future, and this trend mirrors that of the expansions of the electric vehicle market. So naturally, the ramp-up in production of lithium-ion batteries raises concerns over raw resource availability. So the operating principle of a lithium-ion battery is based on reversible redox reactions between the anode and the cathode, and charge balance occurs based on the transport of lithium ions between the two electrodes. Now, because the cathode component usually dictates the overall performance of the battery, this is the focus of my research. Now, shown in this table are the chemical compositions of commercially relevant cathodes. As you can see, the cathodes with high energy density, which is desired for practical applications, are known as the NMC and the NCA type. So these involve some stoichiometric variation of 3 elements. Now, as you can see, they are both reliant on cobalt. Now, the issue with cobalt is that it's expensive, scarce, and geographically concentrated. So a promising approach involves increasing the amount of nickel while decreasing the relative amount of cobalt. Now, this will actually net us a higher charge storage capacity. However, the lowered cobalt content will severely degrade the stability of the electrode. So hopefully my research can solve some of these main issues through controlling the morphology of the electrode and applying appropriate coatings. For instance, increased side reactions between the electrode and electrolyte. Now, these are usually a function of the interfacial area between the two, so morphology control can help tailor this. Moreover, you can also apply a protective coating to reduce the amount of these side reactions. Now, with higher nickel content, you get increased volume changes with lithium entering and leaving the particles. So when you have agglomerated small particles that have increased volume expansions and contractions, this is going to create a lot of crack propagation throughout your electrode. So hopefully you can tailor the morphology to avoid some of this. You could also apply a coating to serve as some sort of glue in a sense to hold the particles together. Now, aspects like thermal stability and moisture sensitivity are also functions of the electrode surface area, so this can be tailored through morphology control and coatings. So exploring the range of applications is the focus of my research. I'll also be looking to other classes of cathodes that are completely unreliant on cobalt.